Hey everyone, this is Everett, and I am hoping to have a nice interactive workshop with you guys about, starting from basically nothing and getting to the point where you're proving things with K. Because there's a long learning curve from starting from nothing to getting to where you're proving things with K, or getting to where you're proving things with anything probably. That means the K definitions we're going to be going over will be relatively simple. We'll just be working with a simple imperative language that we use for testing other things, especially for testing the K itself in the K regression test suite, and also for teaching basic programming language concepts. So that language is IMP, and you can find it in the K programming language tutorial. I'll go over how to kind of build it up from scratch, and then a couple different ways to implement the evaluation of expressions in IMP, because that's kind of one of the trickier parts. And then we'll get to where we are able to actually run some proofs over simple IMP programs. So that's kind of the goal here. Please stop me if there's any questions. The point here is to get everyone at RV, especially people who haven't worked directly with K as much in the past, much more comfortable with the concept of K, and we're talking about proving things with K and stuff like that. So yeah, if there's any questions so far, let me know. This is the repository we'll be working with, so you can go ahead and clone this if you want. You don't need to follow along, but it just contains the solutions, quote unquote, to the various exercises, and then a handful of tests, not so many tests, but just a handful that we can use for making it all work, and then a makefile, which makes some things easier, but is not really needed. So let's go ahead and get started. The README kind of goes through just basically the different lessons that I'm going to go through. The first thing we're going to do is build a calculator, and we're going to add Boolean expressions to our calculator. Then we're going to allow variables to show up in the calculator expressions. And then we're going to, this is where it becomes a kind of imperative programming language, because we add an assignment operator. So here we're just like feeding in expressions and letting it evaluate down to the base value. But here we're actually adding an assignment operator, which turns it into an imperative language with some sort of memory. And then here we have control flows. So that's like your ifs and whiles. So that's going to be where we actually get something that looks like a normal programming language. And then finally, we'll get into procedures, which are where you can define a chunk of code ahead of time and reuse that chunk of code later in some expression somewhere. How's the font size here?
It's fine for me.
Okay. So I'm going to start with this calculator that we want to build. So the calculator, we want to be able to evaluate expressions like this. So like 3 plus 3, I'm just going to put them all out. 5 times 7, 7 over 8 times 2, and 2 to the 4 minus 2. So these are just really simple expressions that don't contain any variables. They don't require any evaluation. We just want to be able to tell K, okay, take these expressions and compute the what they calculate down to. So I'm just going to open up a file called calc.k, and I'm going to clear it because I had it already. And the first thing we need to do is define the modules we'll need. So in K, usually you would have like a syntax module, and then you'd have a semantics module. And the semantics module would import the syntax module. And just for ease of everything, you'll notice that I named this file calc.k, and I named my modules the same thing, just calc and calc syntax, for instance. Okay, so we need to define the syntax for K so that it understands what we are trying to do, basically. So we have to say imports int syntax. These are called K modules, and here we're importing the int syntax module, which is defined in the prelude, which for me is installed at framework, built-in, domains.md. So if you look at that file, you'll see that we have the int syntax module defined somewhere. I have to find it. There we go. Int syntax, which just gives us that, okay, integers are regular expressions that can have a plus or minus at the front optionally, and then any digits that come after that. So it just defines the integer sort and then the regular expression for them. And then I'm going to declare a few operators that are specific to our language, like the plus operator, the times operator, division, other things like that. So I'll say syntax int, which means I'm telling K I want to extend the integer sort with new algebraic constructors, is equal to an int plus some other int. And I'm going to go ahead and make this a function right now. And we can have an int times another int, which will also make a function. And then it looks like we also need division, which will also make a function. I'm assuming that all of this is like not too surprising for anyone here. So I'm going to go ahead and kind of try to go through it quickly. Okay, so all this is done is told K there's a new function symbol called plus, which is infix, you'll notice. So now if we tell K, look at something like 3 plus 3, it'll say, oh, I expect that this function, which I'm kind of using this shorthand to say this function applied to these arguments, applied to the arguments 3 and 3, I expect to be able to simplify out to some integer that doesn't contain this function symbol anymore. But we haven't told K how to simplify that out yet. So let's see if we can actually compile this. So over here on the right, I'm just calling compile calc.k, which by default will compile with the LLVM backend. Okay. And if we want to run a program, we can now say krun. And well, so first of all, look, it dumps in this directory, this calc compiled directory, which contains basically everything that is needed to be able to run programs in this programming language, this calculator programming language, right? So now if we say krun, it will find that directory and be able to, run programs. So we'll say krun tests calc1.calc, which if we remember has the 3 plus 3 in it, but we haven't told it how to actually evaluate the 3 plus 3, so I just want to see what happens, and it crashes. So something about this symbol right here, this core symbol right here, plus uns plus. So I know this is hard to read. I'm not very familiar with reading core, but it's saying, okay, there's some label here, underbar plus underbar underbar. I don't know why it has 2 underbar. Oh, okay, this is the symbol that it's complaining about. So the translation here is that anything in the single quotes right here, you have to treat as an escaped character. So this uns means an underbar, and then the plus means a plus, right? And this is the symbol name that's actually given to this function symbol right here, right? So that's why it gets translated to this weird thing in core, because you can't have underbars and pluses and stuff like that. So it's complaining about not having a rule for how to evaluate that. So we're going to add one. We'll just say rule I plus I goes to I plus int I. And I'm going to try to compile this, and it's going to fail. We'll talk about why. We want to do I1 plus I2. Sorry. But it's failing with a parsing error, and the reason is actually that it doesn't know about the plus int symbol. And that's because all we've done is import in syntax, and we haven't imported int. So in the semantics module, we'll go ahead and import int directly. Yeah. We'll import the int module directly, and we'll say compile calc.k. And it compiles fine, and now we'll try running our 1.calc again, and this time it evaluates down to 6 correctly. Notice there's some other stuff going on here, like these K braces and stuff. We can ignore those for now. The key is that 3 plus 3 evaluated down to 6 correctly. So let's try our second one. And this time it's complaining about the multiplication symbol. So just similarly, we'll give semantics to that. And while we're at it, we'll just do all the other symbols too. Okay. Okay, so we've defined a bunch of mixed fixed syntax functions, and we've told these functions, which we've given no definition to, we've told them actually map them to K's built-in integer operations. So I didn't really go over that, but if you look in the prelude, you'll see that's what I have here is domains.md open. You'll see that like this times int function has been declared. It takes an integer on either side, and it is hooked, which we see as the last argument in the attributes up here to int.mul. So what that means is K expects that the backend, whichever backend it is, LVM, Haskell, Java, whatever, will provide an implementation for this symbol, so that we don't have to provide an implementation in K. We could provide an implementation in K, but it won't be nearly as fast as a hooked implementation. So that's why we hook things like this. And so basically all we've done here is we've said, okay, we want to declare some nicer function names for these functions and then map them to the K unbounded integer arithmetic functions, right? So that's all that's happening here. So we'll go ahead and compile this. And now we should be able to run all of these programs, I believe. Let me check. So 2.calc gives us 35, which is 5 times 7. 3.calc should give us 0 or, oh, okay. So we're missing, so we're getting a parsing error here, right? And what that parsing error is complaining about is this parenthesis right here, because we haven't told K that it's okay to use parentheses in our language. So we're going to go ahead and tell it that. So here we've declared a new constructor, well, it looks like a new constructor for the integer sort that is the parentheses wrapped around some other integer. But then we tell it, hey, this is actually a bracket production, which means remove it at parse time. So if something parses to, parentheses, I'm going to do it like this, apply, no, that's really ugly, 3 plus 3 or something like that at parse time, then the parser will just remove the parentheses and just leave the 3 plus 3. But we can now use the parentheses to force grouping of elements like this 8 times 2 that's under the division sign. We want to make sure that it parses as 8 times 2 and not 7 divided by 8 first. So we use the parentheses to force grouping like that. So we'll go ahead and compile again. Okay, 3 works and 4 works. Okay, so any questions? Could we use different symbols for opening and closing? Yes, you can actually. So we could do these symbols if we wanted, which would mean we have to modify our test, but let's try it. Let's compile first. So now it won't recognize the parentheses, so we have to put in these braces instead. And let's try that. And it worked. You can even do really crazy things like not actually have a bracket or have brackets that have different, are unbalanced or have different different non-terminals on either side of them. So here, for example, we've forced our bracket production to be, oh, now it's getting a parsing ambiguity because it's not able to actually resolve it. So see the division. So see here, the parsing ambiguity is this. In one case, it says, hey, I could have the multiplication on top of the division, on top of the 7 and the 8, and then on top of the 2. So that would be, I'm adding the parentheses here, even though it's not valid syntax in this current language. So it says, now this is a valid parse, and this is a valid parse, basically what this is saying. So not having the closing one actually caused it to have parsing ambiguities again, so it's not a very useful bracket production. But we could, for instance, just use any, like the point I'm trying to make is with the bracket production, the only restriction on it is that there's exactly one non-terminal in the production here. So this is a non-terminal and this is a terminal. Terminals are where you have an exact string that has to be matched. Non-terminals are where it's some other sort that you have to parse in that position. And so the only restriction on bracket productions is exactly one non-terminal in the bracket production, and it's the exact same sort as the sort the bracket production returns. And that's the only restrictions. So let's try this. And we'll run that. And that looks good. Okay, so yeah, don't want to spend too much time on these earlier ones, but any other questions? Anything that you saw that you're just like, wow, that's really weird, did not expect that to work? Okay. Then I am going to save this file as calcbool after updating that. Quit, remove calc.k, and we're going to move on to calcbool.k where we want to add Boolean expressions as well. Okay. First thing to do is rename the modules to be the same names as the file name. This is just for case convenience. And remove any compiled directories. Was everyone able to run that definition, or? Put in the chat if you actually ran the definition and you're trying to follow along or not. This is just so I know whether people are trying to follow along or I should just continue with the video. Okay, so calcbool, we want to be able to evaluate expressions like this, which adds things like the equal, greater than or equal, less than, and, or, etc. So this is just a calculator that now also supports Boolean expressions as its part of what it can evaluate to. K does come with a Boolean module already, similarly how it comes with an int module, and so we're going to go ahead and import that so that we can use the good old Booleans. And it's just kind of similar sort of deal going on here. We're just going to say bool. We can have an integer and the less than symbol and an integer, and that's a function. And we're going to do this for all of our symbols that we're interested in supporting. And we want equals and not equals as well. And then we also want and or, and you can add not, and whatever implies, whatever other Boolean expressions you want to be able to add. And just because I know I'm going to need it, I'm going to go ahead and put in the bracket production for Booleans as well, which allows you to wrap Boolean expressions with the bracket, which we'll need for this fourth one right here to be able to put parentheses around this expression, for example. Okay. If you are having trouble keeping up typing and listening at the same time, remember all the solutions are already in the repository, so you can just copy paste the relevant chunks of code that you need directly into. Now there's one problem which is not super important right now, but we need some other sort that encompasses both Booleans and integers so that K doesn't complain when we try to feed it queries for both. Okay, similar sort of deal. We need to give semantics to each of these functions, which is just going to be exactly the same as we do for these pluses and minuses. By the way, one thing that I didn't mention is, K has no conception of what this plus is right here on the left-hand side until you give it a semantics. So we could have easily said that plus actually gets mapped to times and times actually gets mapped to plus, for example, if we wanted to. And then if you were to say 3 plus 3, instead you would get 9 as a result. So just to make that clear, once again, K has no conception of what these symbols are. It's only when you give it semantics that it actually gets a conception of that. So we'll add some rules for these Boolean expressions. So we'll say I less than I goes to, I1 and I2. I1 less than int I2. Yeah, built-ins. If you're using a submodule build of K or something like that, just do find in the current directory -name domains.md, which won't work for me. Otherwise, you can do user include K framework built-ins domains.md if you're doing a global install of K. So that just looks like this. All the other built-ins are there as well. So we have like domains, json.md, prelude.md, some readme, unification.k, so a bunch of different built-ins. If you need a rational number modules, Dejun made a really nice rat.md for us for one of our projects once. So, right, so let's get on with this guy. And then I'm a stickler for lining things up. Probably if I've ever reviewed one of your pull requests, then you'll know that. Okay, and then we need a not equals. And not equals in K is done with this /through equal sign like that, pretty much across the board. Okay, so that's our comparator operators, which are here. And now we can do our and our or. And the operators in domains.md for that are and bool and or bool, which are defined in just the Boolean module. Similarly to how int is defined, we have this and bool operator, which is hooked to bool.and. But you'll notice we also provide K rewrite rules for Booleans for doing symbolic simplification and stuff with. So we're telling the backend, we expect you to be able to handle this symbol specially, but also here's some rules for being able to handle it if you can't. Okay, so that's our definition here. Let's go ahead and compile that. Okay, and let's run some tests. So the first one is 3 plus 3 is less than 8. We expect that to be true. Comes out to be true. The second one is 5 times 7 is greater than or equal to 9. We also expect that to be true. Next one is 7 over 8 times 2 is equal to 4. We expect that to be false because it's 0 is equal to 4. And then we have 2 to the 4 minus 2, which is 4 is not equal to 2, which we expect to be true again. And then the last one, which is a big Boolean expression of 3 is less than 4 and 4 is less than or equal to 3, which is impossible. We expect that to be true, to be false, sorry. Okay, so that's the entire calc bool language, not very complicated, but now we have a a calculator that can handle both Boolean expressions and integer expressions, for example. So here I just ran one of the original calc tests, which was just a pure integer, 3 plus 3, and that is 6. So we can handle both of these things now. Any questions?